orthogonal to that plane. How can you do it? Cross product of any two what?
Points. Oh, you can't do...
These are points, not vectors.
You can make vectors.
You can make vectors, right? So if we create vectors first, let's say we create a vector that goes, let's say, from here to here. All right? Let's say we create that vector. What would that vector be? Okay, what is it? I'm not calling on people today, but I guess that's about to change. Jonathan, where's Jonathan? Jonathan, what's the vector that goes from here to here?
I don't know.
You don't know?
Wait, but you have to add -2 in.
All right, let's move. Hold on, hold on. I'm gonna see who. Aaron? Where's Aaron? Aaron, what's the vector going from that point to that point? 3? -1? 7. That is correct. Yes? You have a question? Okay. So, this is from last class, right? Or was it the one before? Last class, I think, right? If you're trying to get the vector from a point to another point, you start here, subtract. You go that minus that, that minus that, that minus that. Okay. Now, that's one vector. We need another one. Does it matter which one we get? No. Does not matter, actually. We just can't get the same one, and we can't do the one point in the opposite direction. They've got to have different angle between them. So you could, I mean, I think what makes most sense to me is this one. That one right there. So, Audrey, what's that vector? 3. -6. Minus minus. 2. Okay, there we go. All right. So now we have two vectors. Adam? What am I going to do with those two vectors? Cross product. Now, we still haven't answered the question of, does it matter what order we go in? But maybe we can answer that question now. Why don't you take about 25 seconds to a minute to calculate that cross product? While you do that, I'm going to do it the other way around. All right? And let's see what our answers are. So I'm doing mine over here. I think it's been longer than a minute. All right, anybody have it yet? I'll give you a little more time. -42 plus 2. 21, take away 6, 15, but change the sign. -3, take away 18, -21. 40, 15, 21? Or did I mess up something? Who got something?
So how do you know?
Wait, you did it the flipped way, right?
Yes, I did flipped way.
Okay.
What did you get? You get something?
I got 40,
Uh-huh.
-15, -15.
-15, -15?
I got -15.
Hold on, -3.
So 40.
And plus 18, shit. Sorry, my bad. -3 plus 18 is 15. Okay, my bad.
40, negative 15, negative 15.
You got 40.
Negative 15, negative 15.
Did you change your sign of your middle one?
Yeah, I switched the middle.
So you got 40, and then what? Let me see your middle computation. Your middle computation should have been 6 minus 21.
So it's 6 minus
It's always this and this. So it should be positive. You should be getting positive 15 here, and then negative 15 here.
Okay, 6 minus.
So this is the cross product the way that I asked you to do it. Show of hands, how many of y'all got that? Okay? No? You have an issue? Yeah? Okay. We'll trust that this is the answer. And when I did it, I got this. So, what does that mean? They're scalar multiples, but they're not only, they're scalar, I mean, they're exact multiple of negative 1. So remember how we said if you take two vectors and you cross them, you're going to get a vector sticking out like this? Right? You found that one, I found that one. See? So one's pointed this direction, the other one's, but they both are orthogonal, right? To both. If I flip it over, it's the same thing. So it's okay. And to answer your question, like, does the order matter? Yes, you'll get two different vectors, but they have this relationship. That if you take some vector u and cross it with v, that's equal to the negative of v crossed with u. So they are just off. No, that's supposed to be parentheses. They are just off by a sign. Right? Take that, multiply it by negative 1, you get that. Or take that and multiply it by negative 1, you get that.
Would you accept both answers?
It doesn't matter which one you do.
Okay, so
Yeah. Because you're saying find a vector, right, that's perpendicular to both. Agreed? So you could even go further. Would this answer work? Would that answer work?
scalar, so yeah.
Yeah, that's a scalar multiple of that, right? It's that one divided by 5. So they point in the same direction. They have different lengths, but they point in the same direction. So that is perpendicular to the plane. So there's an infinite number of vectors that are perpendicular, because you can just scale them all. All right. Here's a theorem for, we had a theorem for cross products. Now we have a we had a theorem for dot products that was really important. And this is a theorem for cross products. It is not as important, but it is there, all right? So I'll remind you of the theorem from last class. Last class we saw that u dot v, the dot product, was equal to the magnitude of u times the magnitude of v times cosine of the angle between them. That was the big formula from last class. This allowed us to be able to find the angle between two vectors, blah, blah, blah. Now we have a formula that involves the cross product, but you have to be careful because it's not just the cross product, it's the magnitude of the cross product. So remember that vector that's sticking out? If I talk about its length, the length of the cross product vector is the length of one of the vectors times the length of the other times sine of the angle between them. So that is a theorem. So maybe you can help me with this. If I have two vectors and I cross them, I get this new vector, the cross product. The length of that vector is going to be the length of this vector times the length of this vector times sine of the angle between them. So what happens in this case? That these two vectors are parallel to one another. That the angle between them is 0, let's say. Then what happens? Sine of 0 is 0, right? So the length of the cross product should be 0, right? Make sense? What if these two vectors are like this, pointed in opposite directions? The angle between them is pi, and sine of pi is 0 still. Which means that any two non-zero vectors, they are parallel to one another if and only if the cross product yields the zero vector. So this is a way to check whether or not two vectors are parallel to one another. Do we know how to check if two vectors are perpendicular? We just do a dot product, right? If that dot product is 0, we know they're perpendicular. But how do we check to see if they're scalar multiples of one another? Well, one thing we could do is just look at the vectors and see if it's just like doubling each component or something. But you can calculate the cross product to check it too. All right, here's a result of cross products that's kind of nice also. And this has always just blown my ass away. I'm sorry, it just has. This theorem here. The magnitude of the cross product. So again, give me two vectors. Bring them together. Cross the vectors. Create this vector. The length of that vector is equal to the area of the parallelogram formed by these two vectors. What? What the hell are you talking about? Okay, so if I take two vectors, try and do this here. This is not working out good. Let me make this longer. That'll work. All right. Do you all see the red and black vector? See the red and black vector? Okay. If I were to take the black one, put it here, take the red one, put it here, I would create a parallelogram. That parallelogram, it doesn't look like it's a parallelogram right now. So I'll skew that one over. I hope that you can kind of see that bluish region looks like a parallelogram. Yes? Okay, it turns out that the area of that parallelogram is the length of that cross product vector. It's how long that vector is equivalent to the area of that. That doesn't seem like it would be, but that's what it is. So watch what happens. If I start to shrink one of these vectors down, oh, I didn't tell you what the green vector was. Do you know what the green vector is? That's the cross product vector. Okay, I put it here. So what I'm going to do is try and shrink one of these vectors down. That's not working. There. Let me see, I think I need to bring this one in. There we go, I'm shrinking it. Oh, here comes the cross product vector. See, it's getting smaller? That's because the area is getting smaller. Start making it smaller. Making that area smaller, trying to make the area smaller. Making it bigger. Got too much shit going on here. Damn it, I want it to get smaller, not bigger. There we go. It's getting smaller. There we go. I'm shrinking them down now. There we go. Okay. Get the idea?
The green line is the cross product?
Pardon? The green one is the cross product vector. But the length of it is the area of that. So as that area got bigger, notice that the green one was getting longer. So what happens, what happens to the area? So here's two vectors, right? We can do the cross product. We have this vector sticking out. If we form a parallelogram, which would go like this, do y'all see the parallelogram here? That area is equal to the length of this. So what happens is this starts to get smaller, is this starts to get shorter, right? And what happens when they're right on top of one another? The area is 0, and we just said that when you take the cross product of two vectors and you get 0, right, the 0 vector, it corresponds to 0 area. Now how is this useful? Do we all know how to find the area of a triangle? We all know that, like in pre-cal, if somebody gives you a triangle, it doesn't have to be a right triangle. Let's say someone gives you a triangle in pre-cal, and you want to find the area of it. You would need to know this height, and you would need to know the base, and then you could use area is 1/2 base times height. Now there's other formulas that we had in pre-cal in Cal 1 where sometimes if you just knew two sides, like if you knew that side and you knew that side and you knew the angle between them, then you could use this formula. Area is 1/2 AB sine theta. That's a formula that I know I use in my Cal 1 classes. Do these kind of look familiar? These are the formulas for finding areas of triangles on flat sheets of paper. What about a triangle sitting in three-dimensional space? Right?
Would it be half the cross product?
It'd be half the magnitude of the cross product. Right? So think about these are the same points we had earlier, isn't it? I had those 3 points up here earlier. And it formed a triangle. And we found the cross product, didn't we? What was the cross product? You did it one way, I did it one way, right? Let's go with yours. The cross product of that vector and that vector we got was it 40? 40, 15, and negative 15. That's what you got, right? That was the cross product of those two vectors. So if we call this vector u and this vector v, then that's u cross v. So the area of this triangle is half of the area of the parallelogram. So you have to imagine the parallelogram would go like this, right? So the triangle is half of that. So what we do now is we just take the area of this would be half of the magnitude of the cross product vector. So we just need to take the magnitude of that vector, right? And then take half of it. So this would be half of the square root of 40 squared plus 15 squared plus negative 15 squared. Whatever that is, I won't do the rest, but it comes out to something, all right? I don't know, I mean, if that doesn't get you kind of, well, I don't know. I mean, just think about how difficult that would be without vectors, without cross products. Give you some arbitrary triangle in three-dimensional space and then ask you for its area. It's just, it would be very difficult to do. Very difficult. But we can do it as long as we have 3 points. That's all we need. Give me the 3 vertices. I'll create vectors. I'll cross them. I'll take the magnitude. I'll take half of that. I'm done. And there's no calculus there, right? I mean, there's zero calculus here. This is just arithmetic. That's all it is. Add, multiply, divide, square root. Now, this is even crazier, is if you take 3 vectors, okay? So I now need a third vector. And this third vector is not the cross product vector. This is just, I've got 3 vectors, I bring them all together. Okay? So I bring all 3 of these vectors together. These don't have to be orthogonal to one another. And then I create a 3-dimensional solid, which is called a parallelepiped. Do I say that here? Yeah. A parallelepiped. It's like a shoebox, but all the sides don't have to be perpendicular to one another or parallel to one another. They can be tilted. Let me see. Let me see how my picture is here. Yeah, that's not bad. Okay. So look, do you see the 3 vectors create this 3-dimensional parallelepiped? So like these 2 vectors create a parallelogram. These 2 vectors create this parallelogram. These 2 vectors on the right here create that parallelogram. And if you kind of imagine just kind of projecting through, you get this 3-dimensional solid, right? Yeah?
So basically, the third vector you added would give depth to the parallelogram.
Give depth to the parallelogram. Exactly. So like, yeah, if you have, let's say these 2, right? We had that parallelogram, and then this one just says drag that through and give it depth. Yes. We can find the volume of that easily by computing this. So what you do is you take any 2 of the vectors, doesn't matter which ones you take, you cross them. Okay? That answer is going to be a what?
Vector.
A vector. That's going to be a vector, right? Then you take that answer and you dot it with the other vector, and that will be a number, and then you take the absolute value of that, and that's the volume of it. So I'm not proving these formulas, I'm providing them for you. Again, I think that's just, wow. That's called a triple product. We're not going to do this example. I give you 3 vectors. I'll just walk you through what you would do, right? You go here and you would cross 2 of them. So let's say we take that one, cross them, right? Cross those 2. Then take that answer, dot it with that. Take that answer, take the absolute value, and you're done. So one application of cross products is the idea of torque. So if we tighten a bolt by applying a force to a wrench, then we are producing a turning effect. You know what? I should say something before I do this. Who walked out? Audrey? Wrong time to walk out. Do you remember the right-hand rule?
Yeah.
Okay, right-hand rule. And when we draw our x, y, and z axes, x curl towards y, this is going positive z, right? The cross product works the same way. If I take the vector u and I cross it with v, okay, so bring them together, u cross v. If I'm doing u cross v right now. If I take my fingers on my right hand and I point them down u, all right, so that they curl towards v, the cross product vector will be pointed in the direction of my thumb. So u cross v points this way, all right? V cross u, I got to get on this side. V cross over to u this way. So remember how when we just did that problem a second ago, you got one answer, I got the other, but they were pointed in opposite directions? That's because the right-hand rule. If you go this way, u to v, there, v to u, there. Make sense? Okay, so that has to do with torque. You just missed the most important thing. It was important, right?
Very.
Just make sure you do look at that, like right around 222. Here, I'll jump through the screen so you can go back and watch it. All right, so in physics, we define something called torque. So torque is defined to be the cross product of 2 vectors. So we use this for our torque. It's a vector, and it is equal to r cross f. Now, what is r and what is f? R is the position vector of a rigid body. In other words, we have like a wrench, right, that you're going to turn a wrench on a bolt. So r is the position vector of the rigid body, and f is the force acting on the wrench. The direction of the torque vector is determined by the right-hand rule. Further, the magnitude of the torque is the magnitude of the cross product, which is this formula which I showed you a little while ago, came from a theorem, right? So here's a picture of torque. Maybe. There we go. So if I sit here and I have a wrench. Okay, see my wrench there? I can make it longer or shorter. And then I apply a force to it. So it's like, imagine I'm going to grab this wrench with my hand and I'm going to pull in the direction of this force. So if I pull like this, then I'm pulling on the wrench like this, yes? Then the cross product of those 2 vectors is the torque, right? The cross product. So let's just see what happens. If I were to take the black vector, which is r, and I take the red vector, which is f, and I put them tail to tail. I kind of exaggerated that a little too much. By the definition, torque is defined to be r cross f, right? R cross f. So if I do r cross f, then right-hand rule, right? R, fingers pointed down r, curling my fingers towards f, right? The torque vector would be pointed in the direction of my thumb, which would be going which way? Into the page. And as long as this bolt that I'm turning is threaded as right-hand thread, because there's right-hand thread and left-hand thread, as long as it's like a standard bolt that we're all used to, righty-tighty, lefty-loosey, then as I turn, as I pull here, right, then I'm going to have force into the board. It's going to want to pull the bolt in. Does that make sense? All right. Now, imagine the vector. Imagine the vector that is, here's my black vector, here's my wrench, right? Here's, so imagine as I pull with that force and this starts to turn, the torque vector is going into the board. The length of that, right? The length of that is the measurement of the torque. Okay, but torque technically is a vector, but you can measure its length also. Now, what do you think is going to happen to my torque if I start pulling with the same force, but I start closing this angle like that? Is my torque getting larger or smaller? So you can see it right here. Here's the torque vector, but here's the magnitude of the torque. And you can see that as I'm trying to keep my length of F the same, but notice how the torque's getting smaller? Right? And what happens if I go parallel to that? Torque is 0. You're the idiot. You're just sitting there pulling on the end of the wrench, like straight into, right? You can get fired for that. Where do you want to be to get maximum torque? Why though? Why? Because sine of 90 is 1. Right? Sine of 90 is 1. And if you go back to this formula, the magnitude of the torque is simply the magnitude of R and the magnitude of the force. The magnitude of R is the length of your wrench. That's not changing. Your force, if we're applying the same force, then this is being held constant. Then this is the only thing that's impacting the torque. So you want that to be as big as possible. But it's a sine function, so the biggest it can be is 1. And that's only going to happen at pi over 2. So you want to be pulling perpendicular to your wrench. And then you can pull the other way, right? If you pull the other way, what happens? Well, now your torque is going to start coming out of the page, right? All right, right-hand rule would change things. All right, that's torque. And that's it for that section. At 13 minutes. It's the last day of the week, so we're going to go all the way. I need to pass the sign-in sheet around. Let me see, your take-home. You can do, on the take-home, you can do everything except 6. Yeah. So this take-home, if you're, remember, I give you 8 of these this semester. You are to complete how many of them? 3, any 3, right? I'm going to say that if you turn this one in, you only have to do up through 5, but you will have to turn 6 in later. I'll tell you when 6 is due. But you will be almost done with this, all right? So let's say 1 through 5 is due Monday. Monday, if you're going to do this one. If you don't want to skip this one, you can. There's no bonus for early or anything like that.
Like, no, I meant not the test early. The last question, if we turn it in, number 6 with the rest of the test, managed to like get it before.
Nah.
No.
No. Sorry. Because I don't know if that's going to work out like that later with other tests, and then it's going to just get complicated. And all right, so we just finished 10-4, 10-5. All right, we have about 12 minutes. Let's get signed in here. Here you go. Equations of lines and planes. All right, so we got to get something clarified first. before I can proceed with this. If I give you two vectors, I'm going to call this R0 and R1. If we compute R1 minus R0, the resultant vector is equivalent to the vector from the tip of R0 to the tip of R1. Okay, what? All right, let's say I have two vectors. Let's call this one R1, and let's do another vector. We'll attach them R0, like that. If we compute R1 minus R0, the resultant vector is the vector from the tip of R0 to the tip of tip of R0 to the tip of R1. So this right here is the vector R1 minus R0. Now let's try and understand why that's true. All right? So let's do this. Do you agree that R1 minus R0 is the same as R1 plus negative R0? That subtracting R0 is the same as adding the opposite. Yes? Okay, so let me draw for you this vector. Negative R0 is that vector pointed in the opposite direction, right? That's negative R0. That black vector. And now if I'm taking R1 and I am adding to it that black vector, like this, if I'm going to take R1 and add this vector, then I have to attach this one to the tip of R1. So imagine taking this, sliding it up, and attaching it right here. You would get that's negative R0, right? Do y'all see that? So R1 plus R0, negative R0, would mean start here, go through R1, then add to it negative R0, you would end up here. So the result of that would be like starting here and going up there. Agreed? And that vector is the same as that vector. Is that good enough for you? Sure? Okay. Because I can just slide that over. So if you have two vectors and you want to subtract the two vectors, the result is just the vector going from the tip of that to the tip of that. All right, I need that to be able to do what I want to do next. All right, so we're all familiar with lines, right, from our math classes in the past. A line is a collection of an infinite number of points, right, but they all lie on a straight line. And we have equations for lines. Y equals mx plus b, right? And we've been happy with that our whole lives. Right? It gives us a slope, y-intercept. We've played with that all the time. We are now trying to find a new way to draw a line using vectors instead of using y equals mx plus b. And here's how we're going to do it. So imagine that for this line, I have one point down here. There's a vector that goes from the origin to that point, right? There's some vector that goes there. And for every point on that line, there is a vector pointing to every point on that line, right? So if I can come up with a way to draw all these vectors, I'm essentially drawing the line. Would you agree with that? So if I have some way of having a formula where I plug something in and it draws one of these, and I plug something else in and it draws another one. If I plug in all the different values of some variable in, it draws me all the different vectors, but they all lie on that line. Then I will have created this new equation using vectors to draw a line. So here's how I'm going to do it. Here's how we are going to do it. So the equation of a line is an equation which generates all the vectors from the origin to every point on the line. There's infinitely many vectors. So here's the way we're going to begin. Let's say that we are given, to start with, a point on the line. So we have a point on the line. And that line, that's given to us, all right? Given a point on the line. We call it x0, y0. So a good old point from college algebra. We have 1 point on the line. Then first of all, if I convert this to a vector, then that vector definitely points to that point, doesn't it? I mean, it goes, like that's the point, x naught, y naught, but this is the vector that goes from the origin there, right? So that vector points to that point. And I'm going to call that r naught. All right? Now, give me another point on the line. All right? So give me another point. Do you remember in college algebra, you were asked maybe at some point, like, what do you need? What's the minimum amount of information you need to define a line? 2 points, right? Now, you could also be given a point and a slope. That would be good enough. But 2 points would suffice, right? So let's say that we have another point on the line. So we're given a point on the line. We generate this. Given another point. Given a second point. Let's say that that point's x1, y1. Let's create a second vector. R1 equals the vector x1, y1. Okay? So now that vector goes from the origin to the second point. Do you know what I'm about to generate now? I'm going to now create a vector that is r1 minus r naught. Okay? So now take a look at this vector. I'm going to call it v. And v is going to be r1 minus r naught. Now that vector v, you have to do, this is what I drew earlier. But at the end of the day, I said that r1 minus r naught, that vector is a vector that goes from the tip of r naught to r0 to the tip of r1, right? So in our picture, it's actually that vector, isn't it? So someone gave me 2 points. I created 2 vectors. I did this vector minus this vector, and that gave me the vector going from here to here. Yes? Now, what is it about that vector that's going to be so important to us? I mean, look at it. Where is it? It's on the line, right? I mean, it's on the line. It's parallel to the line, isn't it? It's pointed in the same direction as the line. So what would happen now if I have, well, you know what? Let's look at this. No, it's all right. So what happens if I go and I take r naught? What if I ask you to take the vector r naught and I add to it twice the vector v? So think about what you would do. If you start here at the origin and I ask you to do r naught plus 2 v's, you'd go r naught, then you'd go v, and you'd go twice v, and you would end up here, wouldn't you? So you would have a vector that goes from here to here. And then what happens if I do r naught plus 3 of those? I go farther down the line. What if I do r naught plus half of v? It would be like this and then here, right? What if I do r naught plus negative v? I'd be down that way, right? So essentially this is happening. Where's my damn picture? Oh, here it is. I can basically say that if I just let this be some variable in front of v, let's just call it t, and let t take on all real numbers, then I'm going to be starting out at r naught, right? There's r naught plus nothing. Then r naught plus different multiples of v will stretch me out that direction. Then r naught plus different multiples of v but negative would go in that direction. And so it's like I'm starting with some initial vector, and then I'm taking a vector that's parallel to my line, and I'm stretching it in both directions using a scalar multiple. Y'all follow that? And so what we get at the end is a final version what we call the vector equation of a line. And this is the formula right here. It's that one right there. It says we are going to have a bunch of vectors. All these vectors are going to be functions of some t. And it will be, first of all, a vector that comes, where did this vector come from? R naught came from some initial point given to us, right? So we will create a vector from an initial point given to us, and then we will have t plus t times a v vector. Now this v vector, where do we get that from? R1 minus R naught, right? We subtract the two. That's how we get v. This vector right here is called the direction vector, or the direction of the line. Does it make sense that it would be called that? It's parallel to the line. Why can I not, I guess, why do I have to have R naught in here? Why can't it just be TV?
Because you need a second point to form a line.
Okay, this would form a line though, right? This is all the scalar multiples of a vector. So it would go in one direction, then the other direction. This would form a line, right? Why is the R naught so important?
Puts it on the line.
It actually moves it to where we want the line to be. Because if I just go TV, then at t equals 0, we're going to be here. And then we're just going to draw a line through the origin. But maybe our line's over here. So what we need to do is start off here and then draw our line. So the R naught gives us our initial position, and then the TV draws it. And that's where we have to stop. Yeah. All right, everyone. Did everyone sign in? I didn't call on everyone today, I'm sorry. But you signed in, yes? These weeks are just going to blow by, I'm telling you. Maybe not for you, but